Today we're going to talk about similarity. When two figures are similar, their corresponding angles are congruent and their corresponding sides are in proportion. There are three ways to prove that triangles are similar to one another. The first way is side, side, side. Two triangles are similar if all their corresponding sides are in proportion. So it's basically the same as scale factor. From 3 multiplied by 2 to get to 6, 4 multiplies by 2 to get to 8, and 5 multiplies by 2 to get to 10. They all are in the same proportion. Side-angle side similarity is when two angles are similar if an angle is congruent and the two corresponding sides that include that angle are in proportion. So here, 6 times 1/3 is 2, and 12 times 1/3 is 4. So again, because it has the same scale factor and an angle included between those two sides, these two figures are similar. And the last way is called angle-angle similarity. Two triangles are similar if two corresponding angles are congruent. If two angles are congruent in a triangle, then we know that the third has to be congruent because the sum of the angles in a triangle is 180 degrees. So because of that, if I only have two angles, then I know the third is equal, which is why angle-angle similarity only requires 2. Let's look at this first example and see if we can determine if these triangles are similar. So I have angle LKM, RQS, and NPO. So the first thing that I'm going to do is I'm going to actually highlight in different colors my smallest side of each. So in the first triangle over here, my smallest side is 6. Here it's 10, and over here it's 3. Then I'm going to go with a different color, and I'm going to highlight the medium sides of each. 15 is the medium side, 25, and 5. And then I'm going to go with the large side of each, 18, 30, and 7. So now I'm going to set up a ratio that compares the scale factor of each side. So starting with triangle on the left, let's start with triangle LKM. And we're going to compare that to triangle RQS. So I'm going to keep all of the sides of triangle LKM on the top when I compare these, and all of the sides of RQS on the bottom of my ratio when I compare the two. So let's start with the smallest side of each. So in LKM, the smallest side is 15. In RQS, the smallest side is 25. Now I can reduce that. They're both divisible by 5, and I get the ratio 3:5. Now let's compare, oh, sorry, that was not the smallest side. That was the medium side of each. Sorry, let's compare the smallest now. In the first triangle, it's 6. In the second, it's 10. Those are both divisible by 3. Oh, by 2. Oh, my goodness. And I get the ratio 3:5. Oh, my goodness. Now let's compare the corresponding sides of the largest sides, 18 to 30. These are both divisible by 6. 18 divided by 6 is 3. 30 divided by 6 is 5. So because all of these are in the same ratio of 3 to 5, they have the same scale factor, which means that triangle LKM is similar to triangle RQS. Now, the way that we name them does matter. When I say LKM, I go from L to K and then over to M. So down the pink and across the yellow. And I would have to do the same thing. So starting at R, down the pink and across the yellow to name them. Okay. Now we're going to need to, it says which two are similar. Let's try to see if there's another pair that are similar. Because LKM and RQS are similar to one another, if NPO is similar to one, it must be similar to the other. So let's try. Let's see if we can compare triangle RQS to triangle NPO. Or if you want to designate them, triangle 1, triangle 2, and triangle 3, that could also be really helpful in this question. So let's try, to set up a ratio to compare them. So again, we're going to start with the smallest side, the actual smallest side this time. In RQS, it's 10. In NPO, or triangle 3, it's 3. 10 and 3 do not share a common factor, so that is in simplest form. Now let's try another set of sides. Let's go with our medium sides, which I had highlighted in blue. 25 and 5 are the corresponding medium sides. They do have a common factor. They are both divisible by 5. And this reduces to a ratio of 5 to 1. Now 5 to 1 and 10 to 3 are definitely not the same ratio, so those two triangles are not similar. Now let's talk about how we would read similarity statements. If ABC is similar to triangle A prime, B prime, C prime, which angles would be congruent and which sides would be in proportion? Well, there are two ways to do this, and we've talked about this potentially in the past. One way to tackle this problem is to line up the names. So basically, I would take triangle ABC, and underneath that, I would take triangle A prime, B prime, C prime, and I would line them up. And I like to highlight them when I line them up so that I can easily see the corresponding parts. So angle A is going to be congruent to angle A prime. Angle B is going to be congruent to angle B prime. And angle C would be congruent to angle C prime. Now it says which sides are in proportion. So if I have side AB, that would be proportional to A prime, B prime. Side BC would be in proportion to B prime, C prime. And AC, if I can squeeze it in somewhere, here we go, would be proportional to A prime, C prime. Our other strategy when we do this is to draw a picture. And I like to draw a diagram a lot. So let's draw two triangles. One of them is DOG and the other is CAT. Now, because we drew our triangles, we put the corresponding parts in the same position. So it actually helps us a lot when we go to determine the corresponding parts and which sides and angles go together. So, which angles are congruent? Angle D is congruent to angle C. Angle O is congruent to angle A. And angle G is congruent to angle T. Now, which sides are in proportion? If I have DO in one triangle, that corresponds with CA in the other. If I give you OG in the triangle, in my other triangle, that would correspond to AT. And then lastly, if I had DG, you would tell me that that corresponds to CT. Now we're going to do a couple problems with algebra relating to corresponding sides and angles in similar triangles. So in these cases, we're going to find the missing length, and we're going to use a similarity statement to set up our proportion. So here's our similarity statement. DEC is similar to triangle DHC. So again, I can line these up and use a highlighter to help me. D and G are corresponding angles. H and E are corresponding angles. And angle C corresponds to itself. So now I'm going to identify our corresponding sides. So D and to C in one triangle matches up to CD in the other. Now this is why color coding kind of comes in handy. Or you could do it like this. I kind of like it this way better. If I look at DEC, I can go from D up to E with a squiggly line and over to C with like a thicker line. And then I'm going to read my other triangle name, G to H with a squiggle, and then over to C with a thicker line. Now, in each of the triangles, the squiggly lines are corresponding sides, the thicker lines are corresponding sides, and the sides that are not, don't have any markings on them are also the corresponding sides. So 169 corresponds with this question mark, which we're going to put an X in for. And the 60 corresponds to the 156. So I can set up a proportion to show that those corresponding sides are in proportion, and therefore I can solve for X. So I can put 169 over X because those are corresponding sides, and that would be equal to 156 over 60. Now you do have to be a little bit careful because you have to remember that one of the triangles always has to be consistent with which one is on the top and which one is on the bottom. So now I'm going to use my cross multiplying, my means extremes. And I'm going to multiply 156 times X to get 156X. And that's going to be equal to 60 times 169. When I multiply 60 and 169, I get 10,140. And then to get X by itself, I divide by 156 on both sides. And I would get X is equal to 65. In my next triangle, I'm going to do the same thing. CDB. So I'm going to use my pencil. I'm going to go from C down to D with a little squiggle, and then over to B with a thicker line. And then I'm going to do the same thing in my other triangle, S to R with a squiggle, and then over to T with a thicker line. And now I can see that my 15 and my 55 are both on that squiggly line. And my x minus 3 and my 77 are both on the thicker line. So those are corresponding parts. So if this is triangle 1 and this is triangle 2, I can set up a ratio comparing 15 to 55. Then I need to go back to triangle 1, 3x minus 6 to 77. Now I'm going to use the product of the means and the product of my extremes. 55 times 3x minus 6 should be equal to 15 times 77. I have to distribute 55 to 3x and to negative 6. I get 165x minus 330, and 15 times 77 is 1,155. To solve this equation, I would add 330 to both sides. I get 165x is equal to 1485. Divide to get x by itself. And x is equal to 9. That's all we're talking about today for similar figures and similarity off of the coordinate plane. Please let me know if you have any questions, and